Welcome to the UGC lecture series. This is the E-PG Pathshala lecture series on data structures, and in this module we are going to look at the implementation of the stack ADT. In the last module we had looked at the concept of stack and how stack can be defined as an ADT and the importance of stack in computer science areas. But here we are going to look at the implementation of stack. As we already listed last time, there are 3 possible implementation of stack which we will look into detail in this module. So, these are the people responsible for the creation of this module, and these are the learning objectives. So, we are going to discuss the different implementation of the stack ADT, and here something special in the array based implementation, as we already discussed before, there is something called a stack full condition. So, we are looking at something called a growable array and another concept called as multiple stacks, that is a number of stacks being implemented on the same array, and we are going to look at the linked list implementation of stack, and we are going to discuss the implementation of the stack ADT using another ADT, the list ADT. Okay, so, those are the learning objectives of this particular module. So, let us look at the implementation of stack. Any implementation of stack could be an array or a linked list. This we have already discussed in the last module. If you say array, it is static because the size of the stack is defined beforehand, and dynamic or linked list whether it never becomes full, because theoretically you can take any number of nodes from the memory to create the linked list or increase the size of the linked list. So, we will explore these implementations. So, first let us see how to use an array to implement a stack. So, this is the implementations which I have already seen in the last module, but just to give you a feel, this is the array, physically and conceptually the same. This is the linked list, physically not next to each other, but conceptually they are next to each other. This is the ADT list, it is a little different problem, we will discuss it. So, let us first look at the array implementation of the stack ADT. So, array implementation, any array implementation, we need to declare an array size ahead of time. Ahead of time means during compile time, and associated with each stack, as you remember, the stack is accessible only at the one end, the restriction is that, and that is called the top of the stack. So, for an empty stack, you set top of stack to -1 for this. There are many different types of implementations, but here we are assuming that for an empty stack, the top of stack is equal to -1. So, the stack grows from in the array from 0. Push, basic conceptually what do? You have to increment the top of the stack by 1 and set the stack at that top of the stack equal to whatever element you want to add, which is x. Pop, you return value whichever is in the top of the stack. Remember, this is the address into the array, and you decrement top of stack by 1. These operations are performed very fast and in constant time. That is the advantage of the array implementation. So, attributes of the stack is, here we have to give max size, the maximum size of the stack. Remember, it is a static implementation. So, beforehand itself you have to estimate the size of the stack. Top, the index at the top element of the stack, and S, an array which contains or stores the elements of the stack. The operations of the stack is empty. This is similar to or almost same as what we defined in conceptually. Returns true if the stack is empty, else false. Is full, returns true if the stack is full, else false. Now, this is full is only specific to the array implementation. Remember, when we talked about ADT, we said that we do not have to know the implementation. So, there is no need, you can just take it as a black box, but if you say is full, everyone will know that what we are talking about is a array implementation. So, basically this is full is only specified for the stack ADT, which is implemented with arrays. Top returns a top element of the stack. Remember, it is an access operation. Push adds an element to the top of the stack, modification operation because it changes the stack. Pop deletes the element at the top of the stack, may return the element, may not return the element, but the stack is modified. And display stack, this is another operation that is quite common, prints all the data that is available in the stack. So, let us look at an array based implementation of a stack. Okay. So, array based implementation of a stack is an array S of items of type stack item type. So, we are just naming the type of item as stack. Of course, here they are just integers. So, this is an array which starts at 0, and this is max stack -1, the number of because it starts at 0. This is the maximum size of the stack. that is defined. So, depending on the user telling that this is the maximum number of items that is currently going to be used or whatever, we will define it as the size of the stack. These are called as array indices. Any array has an indices. This is the top. Okay. Here the top points to the topmost element, in this case 2, and items is these items. So, this is the array based implementation of an ADT stack. Now, let us first create a stack. So, the constructor of stack, you have to allocate a stack array S of size, whatever size you want, say size is equal to max size. So, that is the first thing you will do, you will just allocate a stack array of size max size. Okay. So, that is the first thing you do, it is just an array allocation. Then initially you have to take set top is set equal to -1. This is this particular implementation uses that way. So, -1 because the stack first element itself comes to 0. So, that is why you are setting it to equal to -1. This is the initialization, and it means that the stack is empty. So, if you want to check stack empty, if top is equal to -1, you can know that the stack is empty, okay, in this particular implementation. When the stack is full, top will have a maximum value, that is size size -1 or max size -1. So, when the top becomes max size -1, you know that the stack is full. So, remember, stack full condition is only defined when the stack is implemented as an array. So, when that happens, if top is equal to max size -1, you know the stack is full. When top is equal to -1, you know the stack is empty. So, that is the creation of a stack. So, in the creation of a stack, what you have done? You have allocated memory and you have set the top. That is the two things you have done. You have allocated the memory and you have set the top. Now, let us talk about the size of the stack. This is another operation. So, we always add the elements from left to right, and initially top is -1. So, what you have to do is you have to first say size is equal to top plus 1. So, whatever the top element is, that plus 1, because you start from 0 no. So, suppose you have 3 elements, then it will be 0, 1, 2. So, top will be 2 and the size will be top plus 1, 3. So, that is as far as size of the stack is concerned. Next we look at pop stack, pop and return the element at the top of the stack. Now, if the stack is empty, it will print an error information. In this case, the return value is useless. So, no point in returning, and you have to decrement top. So, the pop stack operation is as follows. So, is empty, if is empty, that means you can use an already existing operation of the stack, which we have defined before. That is, if is empty, top is equal to -1. If it is so, then you will throw an exception, empty stack as exception. Now, let us assume this is a stack, that is top is equal to 2, max size -1 and so on. Now, else, now what happens? Top is equal to top -1. So, now this top has been changed. Okay. Now, if you wanted to return this 86, then you should have done it before you decrement this top. So, what you would have done is, for example, suppose you want to return stack item, then what you do, S of stack item, S of top is equal to stack item, and then you do the decrementation. Now, decrement points to this element, and that is not the top of the stack before the pop operation was completed. Okay. So, this depends on what you want to do this with the pop operation. In this pop operation, we are not bothered about the element being returned. So, we are not bothered about that. So, we have just changed the top. So, return top plus 1, this is another way of doing it. So, you will get 86. So, this is if you want to return. Now, stack top returns the top element of the stack. Unlike pop, this function does not remove the top element. So, here you just have S of top is equal to that element what you want to return, that is all. So, there is no modification to the stack. Next is push. Push is the operation where you push an element into the stack. If the stack is full, you will print the error information. Again, as I told you, array implementation only stack full condition happens. Note top always represent the index of the top element. After pushing an element, you have to pushing the new element, you have to increment the top. So, push stack happens like this. If is full, then you give a full stack exception, that is top is equal to max size -1. This we have already explained how to find the full. Then, so this is the top is equal to 2. Now, I want to increment. So, what I do, top is equal to top plus 1. So, that is 3, and what I do, S of top is equal to whatever data I want to enter. So, here S top is equal to 77. So, now I have this. So, this is the push stack operation. So, as you have seen, when you want to push, you have to add top is equal to top plus 1 because it is only an array, and if you want to pop or delete, you have to say top is equal to top minus 1. So, as far as this is stack or array operation of stack is concerned, we had an array and we just had to manipulate the top operation appropriately. For a pop operation, we checked if it is empty. For a push operation, we checked if it is full. Now, you would have wondered, normally we do push first and pop next. Why did we do pop first and push first next? Nothing very great about it, because push is a special case as far as array based implementation is concerned, as I already told you. So, the array storing the stack elements may become full in the case of array, and a push operation will then throw a full stack exception, which we already saw. So, limitation, this is the limitation of the array based implementation, and it is not intrinsic to stack ADT, because as far as stack ADT is concerned, whatever may be the implementation, the same operation should be possible. So, if you say full stack exception, that or stack full checking, that particular operation is not possible if it is linked list. It is not viable, it is not, does not make sense if it is linked list implementation. So, that is why we say that this particular operation, a push operation which gives a full stack exception, is not intrinsic to stack ADT. This I have been stressing from the beginning of this implementation module. So, what are the performance and limitations of stack ADT implemented using arrays? Let n be the number of elements in the stack, the space used is only 0n, and each operation will run in time 0 1. So, that is as far as that is the good parts of the performance. Limitation, the maximum size of the stack must be defined a priori before you do and cannot be changed midway. Trying to push a new element into a full stack will give you a implementation specific exception. This is what is the problem. It is an implementation specific exception, and as far as ADT is concerned, we do not want anything implementation specific. So, we go to the concept of a growable array. Now, what is this growable array? So, the case where the array is full is not an exception that is defined in the abstract ADT stack. If array is filled, we have 5 options. Increase the size of the array. So, if it comes full, increase it, throw an exception, which we did. Ignore the element being pushed, forget that push operation is happening. Replace the current top of the stack, that is, keep changing only the current top. Put the pushing process to sleep until something else removes the top of the stack. Include a member function boolean full constant. So, there are some very interesting ways in which we can deal with this. So, what are we talking about? We are looking at dealing with a condition that happens when the stack becomes full during a push operation, remember that. So, increase the size of the array, which we are going to look at, throw an exception which you have already seen, ignore the element being pushed, which is not very nice to do, replace the current top of the stack, which means you are losing an element that is currently on top of the stack, put the pushing process to sleep until something is actually removed, which is a slow process. You may lose information for the application. So, that is what we are going to look at. So, let us talk about array capacity. If dynamic array is available, the best option is to increase the array. If you already have memory, increase the array capacity. Now, if we increase the array capacity, the question is how much should we increase it by? By a constant, that is, make it array capacity is equal to array capacity plus some c, some constant. Say suppose you had 100, make it 120, or by a multiple, suppose you had 100, make it 200. Any time that we push onto the stack requires n copies and runtime is of the order of n. That is, now in a full stack, if you push an element, then if you want it to be implemented with that increased size, you have to push everything. Remember the array operation of inserting into a list. Therefore, push is usually it becomes from 1, it is normally of the order of 1, now it becomes of the order of n, because n elements have to be pushed, but this happens only when a new element is added to a full stack or when new memory is required because of that. So, that comes the growable array based stack. In a push operation, when the array is full, instead of throwing an exception, we can replace the array with a larger one, which we were talking about. So, how large it should be? You can increase the size or you can double, which you have already discussed. So, Like let us look at that. Now, here we have a stack where the top is max minus 1. When the top becomes max minus 1, we know that the stack is full. Now, what we do? We create a new array. The array that we have created is this is size 5, this is size 10. So, which means we have doubled, that is 5 into 2 multiplied by constant and increase the size of the array. Now, the next operation that we have to do is we have to do a loop. What should we do? 0 to top, top is measured here. So, 0 to top do ai is equal to si and make this new stack equal to a. So, now this becomes a new stack. Okay. Now, you have 5 empty locations which you can do insertion into. So, this is a growable stack, okay. But of course, this operation has to be done. So, now compare the incremental strategy and the doubling strategy. Remember, incremental strategy, every time you do a push operation you have to do n again, that is you have to change shift everything. So, analyzing the total time Tn needed to perform a series of n push operations, assuming initially empty stack represented by array of size 1, amortized time of a push operation, the average time taken to push over time over the series of operation is Tn by of the order of total time divided by n. So, this is when you are doing an incremental strategy. So, to state the average run time, we will introduce the concept of amortized time. Let us look at what is amortized time. If n operations require of the order of function of n, we will say that an individual operation has an amortized runtime of the order of function of n divided by n. So, this is just taking a small average type of operations. Therefore, if inserting n objects requires 0 n squared copies, the amortized time is of the order of n. For order of n copies, amortized time is 0 1. So, this is how we will calculate it. It is nothing but the function of n, if it is n squared, then n squared by n. If the function of n is n, then it is n by n. So, that is how you calculate amortized time, generally how you calculate amortized time. So, what we will do is we will replace the array k equal to n by c times. So, the total time Tn of a series of n push operations is proportional to n plus c plus 2c plus 3c plus 4c plus kc, that is equal to n c. So, this is the, remember our analysis of algorithm which we did a little bit. So, n is equal to c k into k plus 1 by 2. Since c is a constant, T of n is of the order of n plus k square, that is approximately n square. So, the amortized time of a push operation is of the order of n. So, this is how you do if you have an incremental strategy. What is the difference between an incremental strategy and a doubling strategy? Conceptually speaking, doubling means you know that you have reached a full and you have done so many stack operations. So, the next time you will do the next doubling only further on, but incremental, you are incrementing by a constant, and the chances of it getting frequent updations requiring incremental array being needed is more. So, doubling strategy replace array k by log 2 n times. So, here instead of having n by c times, you will have log 2 n times, that is the total time Tn of a series of n operations will be now proportional to, remember here it was c plus 2 c plus so on, here it will be n 1 plus 2 plus 4 plus 8 2 power k. So, that will be of n plus 2 power k plus 1 minus 1, that is 2 n minus 1. So, it is of the order of n, and the amortized time is of the push operation is of the order of 1. So, that is the difference. So, if you do doubling, your time is amortized time is of the order of 1, but if you do it in incremental strategy, the amount of time is of the order of n. So, obviously, doubling strategy is better. So, the difference in worst case amortized scenarios, just to give you an idea, if you increase it by 1, the copies per insertion is n minus 1, unused memory is 0, okay, that is also an idea. Increase by n by m minus 1, increase by a factor of 2, 1 n, and increase by a factor of r is greater than 1, it will be like this. So, depending upon, now again which strategy is better depends upon the type of how many push operations that stack is going to undergo in an application period. So, that estimate if you know, you can choose the correct strategy. So, the next, so now we have up to now we have spoken about one particular aspect of array based implementation of stack, that is the full condition, and we spoke about how the full condition can be tackled by either an incremental strategy or doubling strategy, and we looked at amortized time of both and found the doubling strategy is better. Of course, the price you pay for that is a amount of unused memory is more in the case of the doubling strategy than in the case of incremental strategy. Now, we will go to the next topic that comes under specialized, that is again coming under array implementation of stack ADT, that is multiple stacks. So, here you have the bottommost element and elements of stack 1, and this is the we are assuming 2 stacks obviously. So, this is the bottommost element of stack 2. So, more than 2 stacks you can have, and memory is divided into n segments. So, if you have n stacks, it will divide into n segments, and boundary stack number is the 0 stack number less than maximum stacks, and top stack number is so much. So, the idea is that you divide it, for example, if you take 2 m 0 up to half of that, and this is you go this way, this direction, and this is goes in this direction. So, this is boundary 0 top 0, this is boundary 1 top 1, boundary 2 top 2, and boundary n, this is if you have n stacks, and boundary I is equal to top I, which means that the stack is initially the stack is empty. All stacks are empty and divided into roughly equal segments. So, find j stack number less than j less than n such that top j is less than boundary j plus 1, that is the top of, if you can know, the top of 1 will meet the boundary of the next stack, then you know that the stack is full. So, when stack I means stack I plus 1, you know the stack is full, that is how you consider this, that is T I means T I plus B of boundary of B plus 1, boundary or bottom you can also call as bottom, that makes more sense. So, bottom of 1, top of 1, this is the bottom of the next stack, this is the bottom of the top of the next stack. So, when this the top of the first stack meets the bottom of the next stack, then you know stack is full. That is the same as array. Here only advantage is in an array you are representing multiple stacks. So, that is as far as array implementation of stack ADT is concerned. Now, let us look at the linked list strategy of implementing stacks. So, here you have the conceptual and physical stacks. This is the conceptual stacks. Physically, though these nodes may have various addresses spread across the memory. So, this is we have not put the items, but this is a stack of count 4 and top points to the topmost node. Now, let us look at a pointer based implementation required when the stack needs to grow and shrink dynamically. You do not want to waste memory. Top is a reference to the head of the linked list of items. So, it will just like a head of a linked list. Copy constructor and destructor must be supplied, copy to create a node and destructor to remove a node. This is an example. So, let us first create a stack. So, when you create a stack, you create a new node p new and put count. So, allocate memory for stack head, and then second step is set count to equal to 0 and then set top equal to null. So, these are the 3 steps for creating a stack. This particular node you would have seen when we were doing that set of series of operations on stacks in the previous module. So, next we will look at and then return the stack head p new as the stack. So, now the new stack is this. Now, let us look at pushing. So, let us say we want to push stack 45, that is into the stack we want to push an element called 45. So, this is the stack and this is the head and it says 4 and top, and this is the element before the push operation. Now, the first thing you have to do is allocate a new node. So, this is p new, it has data and link, and here you have p new dot data is 45 and p new dot link is top. Okay. So, this link, and so you have here and top is equal to p new, the new thing, and the count has to be incremented to 5. So, this is what will happen, the count will be incremented to 5. This is the new p new, so the top has to point to p new, the link of p new will point to the previous top. That is, you have to do of course this operation before you do this operation, otherwise you will lose the address of stack. So, this is the push operation. Now, let us go to the pop stack operation. So, this is the stack before the operation, and if stack is empty then pop is false, normal operation is empty. So, data out is equal to top dot data and top is equal to top dot link. Now, the new top will point to this. So, that is the, and of course, the count has to be decremented. So, this is the new, so this 45 is given out and the new top points to the address of this node and count has been decremented. So, this is the pop stack operation. Okay. Now, there are other operations that you can do with this linked list or any implementation. So, if count is equal to 0 in linked list, then it gives true, else false. So, empty stack is very easy. Stack top, that is, remember what is stack top? Stack top accessing the top element of the stack. So, if empty stack, then obviously false, you can't access, otherwise stack top is equal to top dot data. Then stack count is return stack dot count, because we have in the head node we have put a count very conveniently. Destroy stack until loop until stack empty, delete top node and delete stack head. You keep deleting, this loop is for the delete top node. Then delete or pop top node. Full stack, if no memory, then true, else false. This does not normally happen in a linked list implementation, as we know, because we assume the memory is available. Now, we go to using the ADT list. So, that is another way of implementing the stack. So, this is interesting because the first time we are using an ADT in an application, that is what we are essentially doing. ADT list can be used to represent the items in a stack. So, if first item is in position 1 is the top, then push new item position 1. So, insert 1 into new item. So, that is this is insert, remember, is a list ADT list operation. And then pop, remove 1, remove the element at the top of the stack. Get top, retrieve 1 comma stack. We are assuming insert, remove and retrieve are available to us as list operations. Now, using ADT list, this is the top of the stack, this is my list and this is the positions of the list which we were using here, insert 1 1 1. So, here because we are representing the list like this, whatever is 1 on top of that will be my access point to the stack. So, I can also have a list dot get length to account for the count. So, I can use the ADT list, list A list will list the stack list of stack items, is empty stack, return A list is empty. This A list is the ADT list, push stack new item will return A list dot insert 1 comma new item. Pop stack, if A list retrieve 1 comma stack top, then return A list dot remove 1, else return false. I will come to this. So, now if you look at this, we are using an ADT list which has the operation is empty, insert, retrieve and remove for implementing the stack ADT is empty, push and pop. So, that is what you have to understand. So, this is empty returns just uses A list or is empty function. Here instead of push we have insert, only difference here is we are inserting always only at 1, because we are only inserting at the top position. So, if you delete something, one will the first will automatically updated in this implementation of ADT list. Here this retrieve 1 comma stack top is the one that we have assumed that the ADT list implementation gives a true or false value. We are assuming that remove does not give that. That is why we are if this boolean gives me a value, then I return A list dot remove 1, otherwise I return false. So, now comparing the different implementation, it is one is the basic difference in implementation is fixed size versus dynamic size. So, in an array based implementation, it prevents the push operation from adding an element if the size exceeds the allotted size. Pointer, there is no limit on the size of the stack. An implementation that uses a linked list versus one that uses a pointer based implementation of the ADT list. ADT list approach reuses an already implemented case ADT list. Okay. So, much simpler to write and saves time. This is true for any ADT usage, ADT data structure usage. So, here please note we have done a different approach to the stack implementation. We have used an already defined ADT list for implementing the stack. So, in this particular module, we have explained 3 implementation of stack ADT, and one particular implementation is interesting because it already uses an already defined ADT list, which we did in the previous modules, and we discussed array implementation of stack, where we discussed 2 special cases, the full stack case where we spoke about growable array and the 2 strategies associated with it, and then we also spoke about how multiple stacks are defined using the same array. Then we explained the linked list implementation of stacks, and then finally we outlined how ADT list can be used in an application of implementation of stacks using that particular ADT. So, thank you very much.